Okay, let's do the list of all real numbers. So let's start first with natural numbers. Natural numbers n. So the list goes like this. It's actually including 1, 2, 3, 4, and so on up to infinity, but not including infinity. So next we are going with integers. That's starting with a 0, then 1, minus 1, 2, minus 2, and so forth up to infinity. And not including infinity. Yeah, so far so good. Next with rational numbers. That's going to be pretty close to like Numberphile was doing. So we can't do with, well, actually, let's do like this. So rational numbers is something like one number divided by another number, and 1 divided by n2, where n1 is from 1 to infinity, and n2 is from 1 to infinity. Right? I'm excluding negative numbers because it's like exactly like with integers, and I'm excluding just like Numberphile excluded the meaning of that rational numbers must be co-prime, meaning that 3 divided by 6 is the same as 1 divided by 2. So only one of them should be included. But if we go with all n1 values and all n2 values, we basically get all possible rational number values. Now, the way they are shown in Numberphile and the way it's written in Wikipedia is something to do with diagonals, like this. 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 4, then 2 divided by 1, 2 divided by 2, 2 divided by 3, and so on. You get the idea. It's actually, you can review the video again or read Wikipedia. But there's a problem with this counting, and I'm going to explain in a second. Yeah. It's a bit hard to write and speak at the same time. Yeah, and it's going like this forever. And downwards as well. And as they explained, we can't go with the first row and then the next row, because the first row never ends. It's actually going to infinity. So we can never list or count the next row. And so it should be uncountable rational numbers. But since it's defined as countable, so be it. So they suggest to go with diagonals, like list this number first, then this, this, and so on. So it's going diagonally, listed diagonally. The problem with this is you can see the whole area of these numbers is just like a big square. Big square. And at the top we have n1 values from 0 to infinity. Yeah. And here we have n2 values going from 0 to infinity. Well, it's actually not 0, it's just 1, but never mind. I'm ignoring the 0 exception, just like co-prime requirement as well, and negative numbers. So just the natural numbers for now. So the problem with diagonal is that we can only fill half of the square going with diagonals, because as soon as we get to the edge of the square, one of the numbers gets to infinity. So we can never ever possibly get to the other half of the square. And we can completely understand it's pretty valid numbers are at the other side, on the other side of the square. So going by diagonals is not the way to go. To list properly rational numbers, we should go by doing like this. List this number first, then this, then go downwards, then go this way. Then this one, down, down, and sideways. So we go like this and increasing one row and column and row, and one at a time. So we can list all the values up to infinity. So we only exclude at the very edge where either n1 or n2 are equal to infinity. So now we could list all rational numbers and they are countable or listable as Numberphile prefers. Okay, so now let's go to real. So how do we define real numbers? I would prefer to write them as such. n1 dot n2, where n1 is from 1 to infinity and n2 is from 1 to infinity. But not exactly. It's kind of, there's a bit trick here. Why trick? And the trick is here, because if we have a number sort of like 23.01, for example, right? So in this scenario, n1 is equal to 23. That's easy. But n2, for any double-digit number or more than 2 digits, we need to flip them horizontally. So instead of 0, 1, which would be equal to 1, we need to flip them and it should be 10. Right? So it's the same with any number, you know, 23.001 or 23.011, for example. n2 would be equal to 100 in this case, and n2 would be equal to 110, right? So we can write any real number like this, with natural number here, dot natural number here. Also including zeros, because 0 can be here and 0 can be here, as well as negative numbers. So because we have just single 0 and negative numbers are exactly the same as in integer numbers, so it's the same. For now I'm going to ignore negative numbers and 0 as well. So the last question is, well, basically we get exactly the same table as here, but instead of writing them as rational numbers, we write them with the dot. So we have, well, we should start with 0, but I'm ignoring 0, so I'm going to write with 1. So 1.1, 1.2, 1.3, 1.4, blah, 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 2.1, 2.2, 2.3. Well, you get the idea, right? I'm not going to write all of them because it's exactly the same table as here. Just it's with the dots instead of a division symbol. So, and exactly we can list them, all of them, exactly like rational numbers. So this is first, this is second, this is next, this is next. This is first, this is second, you know, blah, 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 blah. Yeah, like this. So it's very easy. So how do we know we listed all the numbers and we didn't miss anything? And what about the irrational numbers like square root of 2 or pi, right? So first of all, when the n2 goes to infinity, the precision of number written goes to infinitesimal. So assuming the distance between two real numbers is at maximum is infinitesimal, I think that's the definition of the real number itself. That's at least my definition in my mind. You can verify somewhere else and correct me in the comment section if you have other information. And as for square root of 2 or pi, if you have value which is within the precision of infinitesimal, you have this number in the list. So I think that's pretty much defines that this is a complete list of all real numbers, which is possible. Thank you and have a nice day.